History of atomic structure, a quick timeline. We'll start with Democritus' ideas in 400 BC, John Dalton's billiard or pool ball idea here, 1830, J.J. Thompson's plum pudding model of the atom, 1906, and then more advanced ideas and understandings in the early 1900s when we kind of get to the Rutherford model of the atom and further. All right, so here we go. The idea of an atom is something that was described by the Greek philosopher Democritus around 400 BC, and it means indivisible. So they were hypothesizing about matter, the stuff around us, being composed of little chunks that if you cut down to the smallest of chunks, you would get down to something you couldn't cut anymore. And that would be atomos, or indivisible. It's where the word atom comes from today. Yeah, let's scribble that in for posterity. Atomos. Indivisible. Switch back. It's not really until we get to the latter 1800s and the early 1900s that we really had the equipment to pursue this idea of atoms, these tiny things, because we needed to work with really tiny things, and we needed positively charged particles and negatively charged particles just to find out what the heck was in there. We had to do some probing. So, going back to Democritus, 460 to 370 there, this idea of atomos, indivisible, was philosophical. By philosophy, we talk about coming up with ideas and debating and arguing ideas, but that's not the same thing as using the scientific method and then experimenting and then re-experimenting and learning and writing down the data and figuring out what it all means. But everything does start out with a philosophical idea. Really, we can start with a hypothesis and go from there. So remember, philosophy is about ideas, and the scientific method is about taking a hypothesis and then testing to find out whether or not it is true or not. It takes a lot of work. You've probably heard of alchemy, and you've probably heard about moving from, see if you can transmute lead to gold. That was the big idea, right? Let's take lead and let's turn that into gold. And these are the atomic symbols for those elements. But in order to be able to do that, you would have to mess around with the number of protons in the nucleus of lead. You would either, if you think about it, if you don't quite know where lead is on the periodic table, you would either have to take protons out, or you would have to add protons. You have to look at the periodic table and see where is it in relation to gold. That's not such a simple thing. By today's standards, we do know that elements are given their characteristics by the number of protons in the nucleus. It's their atomic number. So messing around with an atomic number is like going into the nucleus and yoinking protons. Not so easy to do. But the idea was that you could transmute things, right? That you could find the elixir of life, right? That's a philosopher's stone idea. Or something that would dissolve almost anything, which turns out is water, but anyways, it doesn't dissolve everything. The idea that the alchemists weren't important isn't entirely true, because they were using observation and they were experimenting and they were trying things over and over and over again. So they were applying the scientific method, but they just didn't have the level of knowledge to accomplish goals like transmutation, right? Lead to gold, not going to happen. We'll move to John Dalton's discoveries, and let's bring up the pointer here, about 1760 to the other half of the early half of the 1800s, Dalton was studying the structure of the atom. And he thought, well, if atoms are a little bit like Lego, now he wasn't thinking Lego, but I am, you'd be able to bring them together and make new combinations. And he was talking about proportions. Now, here's a simplification, but what we know today, if you think about water, you've seen this structure before, we know that water is composed of 2 parts hydrogen and 1 part water. or sorry, 1 oxygen. I'm getting ahead of myself. 1 part oxygen. So it's a 2-to-1 ratio, like this. Or you can think of it as proportions. Now, this is something that Dalton wouldn't understand at the time, but he was thinking about recipes. Literally, you take a little bit of sodium, you take a little bit of chlorine, and you get NaCl. Right? We know sodium's a metal and chlorine is this greenish, kind of horribly poisonous yellow gas on the right side of the periodic table. This is very early chemistry. So Dalton was coming up with his ideas about how things could come together. And really, that's an idea of taking atoms and, in the end, composing molecules. He was definitely on his way. So, what did Dalton discover? Oop, there we go. Well, his theory, his big ideas were that elements were made of these tiny little indivisible particles called atoms. And that's an idea borrowed from sort of the Greek idea of atomos. And that atoms of the same element are identical. And, let me just bring up my drawer here. If you think about it, hydrogen is composed of hydrogen, and sodium is composed of sodium, and helium is all helium, right? So that's the idea of an element, indivisible particles. Bring them together, come together in new ratios. Well, maybe something like hydrochloric acid. And that in reactions, atoms are recombined, so we get molecules. This last idea here is the idea of molecules. So this is Dalton's theory of the atom. He saw them as these really hard things. I should kind of just scribble that. He saw them as billiard balls, like pool balls, and that everything was inside and they were just hard. So I'll just draw these lines. It's all hard as a rock. That's why they're indestructible. Everything's in there. It's impossible to destroy them. Now, Dalton's atomic theories got people to thinking, right? Okay, so atoms, what if they are these indivisible things made up of, well, what things? Because if Dalton's going to draw a billiard ball, they're saying, okay, so what is in there? Because they have mass. So if it all comes together like a big cluster, are there little chunks inside? And that's where the idea of investigating the atom really took premise, where they go after these things like these subatomic particles. Let's just go back here for a sec. Now, today you know these. Electrons, often drawn like this, right, for shorthand. Protons, positive charge, and then neutrons, because they have no charge, we hit N. By today's standards, you have probably seen in your previous science classes models of atoms, which include all three of these things. But we'll go back a little bit to the point where they had to find them. That's the whole point of this lesson. So, discovery of the electron. This is a cathode ray tube. Okay, that's a fancy way for saying something like a TV or a monitor. So what does that mean? I need to be able to scribble here. There we go. The idea is that you set up your cathode, your negatively charged end, and you set up your positively charged end over here. So the idea is, under high voltage, send an electrical current in this direction, and you get basically a beam of current, a beam of electrons. So this is negative. And what it normally does is it normally goes straight. So I'm going to draw it going straight. And when it hits this plate on this end, in the case of a TV, for example, this plate here would fluoresce. That's kind of how TVs work. But what they were doing is they were just passing these negatives along like this in a beam. But you probably already noticed, it's like, wait a minute, hold on. You've got something there that is a negative. Why is the negative beam trending up like this? It appears to be bending. Well, in a cathode ray tube, and I should point out, it's under low pressure. They They didn't want any. They didn't want the beam running into any particles. They just wanted a clear path. Okay, for example, you wouldn't want a gas in there picking up the beam because the gas could start glowing. For example, if you look up when we're at school and you look at those fluorescent lights, it's kind of like this, and the gas glows, and that gives us our, well, basically our lights in the class. What they did in this case is they removed all the gas because they didn't want that to glow, and they set up another plate here and another plate here. So we've got a positive plate and a negative plate. So they're messing with this beam, and what they noticed it did is it moved up, which meant that this beam, that this current was negatively charged. This proves it. So current, when it's flowing, is just electrons, right? So as those electrons are flowing, right, it's negative charge right here, when it's going to be repelled, right, pretty strongly. It doesn't like this. It's going to be repelling from that plate, and it's going to be attracted to the positive plate. So they're able to get it to veer off course. And this is J.J. Thompson's grand experiment, because he discovered that electrons are negatively charged particles because they're attracted to that positive plate, and they really hate this negative plate. So it's this cathode ray tube experiment of science, and that there's a negatively charged particle out there called an electron. Oops, so we'll give it an E minus, like that. So modern day cathode ray tubes, you probably, I don't know if you saw these in elementary school, you might have, these have been around longer than I have. The idea was you would fire that beam and it would cause the screen to be hit by electrons in patterns, and we would get red, green, and blue pixels to fluoresce and give us a picture. I'm just drawing blue, but what the heck, let's put in the green. Because those are the colors, primary colors that make up everything. We mix them. The human retina has red, green, and blue color sensors. So let's throw in some red for posterity. There we go. Now, mind you, this is for color monitors, right? So they're being hit by electrons, and the electrons are causing them to glow. So this idea has been around for a long time. The idea that the monitors would glow, we got a little bit of radiation. We've since moved on into LED and LCD technology. But it's pretty cool. Now, here's a neat one. If an electron is a particle inside of an atom, then what's its mass? Now, there's a very famous experiment that I can't even begin to do justice because it's its own lesson. So I'll just have to summarize here. The mass of an electron was discovered, proven, in 1916 by Robert Millikan, and he did an ingenious thing. He discovered that the mass of an electron is tiny, and I do mean tiny. Right? Now, if that number isn't impressive enough to you, remember that's to the negative 28th power. So this is a really small element of mass. So electrons do have mass, and he used sort of an ingenious experiment. His oil drop apparatus over here, this is a little plunger, and he basically sprayed oil into the top of a container, and it became little droplets, and I'll show you an animation of this in a second. And he was able to pass them in between two charged plates and determine what the weight of an electron was. This is a little sort of observational peephole where he was observing what happened to the oil particles when they were dropped into the chamber. So I've got a little animation for you here. Let's go over here. Not this one. That's for later. This one. There we can. So in this case, you could see sort of a positive and negative set of plates in the middle, and you could see the atomizer on the right. And when he sprayed in the oil, it made it into really small particles. And those particles fell down that hole on the top plate. Now, when we went through the top plate, and he's viewing from the side, what he was able to do, he was able to give those particles a charge. Now, the charge that they would get, right, when you think about current electricity, only charge that he could really give them would be a negative charge. So he put electrons on them. And without making it too complicated, he learned that the particles had several forces acting on them. One, they wanted to fall down, that was gravity. Two, there's a little bit of static cling, electrostatic forces where the particles sort of want to stick together. And he did a brilliant thing. Between these charged plates, he was able to get the particles to fall. He was able to get the particles to hover in the middle. He was able to sort of equalize forces. But the long and short of this is he had the weight of the particles determined before they entered into the plate, and he figured out the weight of the particles once they had gotten an electrical charge built up on them, and he took the difference. And he was really, really close. So if we go back, he was able to determine that compared to a proton, that the mass of an electron was that ratio. So it was 1/1840th of a proton. Okay, so when you think about atomic mass units, and I'll just draw up here, one proton is equal to one atomic mass unit. It's just simple. You know, it's sort of how we say 1 kilogram. In this case, instead of kilogram, we'll say one atomic mass unit for simplicity. Neutron. Well, later on, with the discovery of the neutron, we learned that that was one atomic mass unit too. Okay. At this time, that wasn't discovered, so we learned about the mass of an electron very, very early on, and it's tiny. It's that much. So, what are you able to conclude thus far? Okay, well, with J.J. Thomson's experiment, we learned about electrons and that they're negative, and then Millikan comes along, and we learn that they have mass, right? So, cathode ray tubes, all of this, they're teaching us so much. But we learned, when you look at atoms themselves, they're not electrically charged. If you're thinking about electrically charged things, we have to talk about ions. So for an atom to be a neutral thing, if there's an electron, right, and that's a -1 charge, if they're neutral, there has to be a +1 thing, right? A charged particle. What was this charged particle? Because if we take a positive charge and we take a negative charge, that's what we expect to see. So, okay, so there's electrons. Then what's the rest of the story? Where's the mass coming from? Because the mass can't be coming from an electron, which is extremely, extremely small, and it has virtually no mass. So just sort of final point, I've kind of already gone over that. So where's the mass coming from? I sense another experiment coming. I just know it. Yep. Thompson's atomic model. So Thomson, his idea is that, sure, we've got electrons, but if electrons are going to be staying together in something, they're probably attracted to some kind of material. So he's surmising that there's positive charges and there's these negative charges in an atom. Now he sort of sees it like pudding. Now pudding is just a term that just means dessert. I actually didn't know that till I was 14. I had a friend, Australian friend, and his parents said, "Oh, when we say pudding, we mean dessert." I was like, "Oh, really? Never knew that." Thanks for the heads up on that one. So the plum pudding model is this idea that electrons are bouncing around and they're attracted to something, and it's a bit like fruitcake, right? The electrons don't like each other, so they bounce off each other, but there's positive things, so that's why they're sticking around. Sort of an interesting plum pudding model. Okay. So J.J. Thomson develops this idea, And it's another step in the right direction, just sort of coming up with a hypothesis, coming up with a model. And then Ernest Rutherford comes along and does the gold foil experiment. Now, this is a very ingenious experiment. So what they do in this case is you're able to not only pass current through things. The cathode ray tube was basically emitting electrons. In this case, instead of electrons, they discovered that they can emit what are called alpha particles, and those are positively charged particles. So let me just bring this up. So this thing is firing a beam of positive charges like this, positive little particles, and firing it. And what they did is they fired it at gold foil, just thin gold foil. And the idea was, is this a bit like golfing? Like, for example, if you ever go golfing and you can't get around a tree and you just kind of look up at the tree, you think, well, you know, a tree's mostly empty space. If I just send the ball through the leaves, maybe it won't run into anything. You know, maybe I'll get lucky, or, ooh, maybe it'll hit a branch and it'll deflect, or maybe it'll hit a really big branch and it'll come right back at me. So the idea was, let's pass particles through here and let's see what's inside. On this side over here, you can visualize, and they were visualizing these atoms, these balls, and they wanted to see what was going to happen when you pass these little positively charged particles through atoms. Would some go through? Would some hit something and bounce back? Would some hit something and sort of veer off course? Interesting question. So before we see the data, let's go here. Not the plum pudding model, but let's look at the gold foil. All right, so what were they doing? In this case, you could see those little red dots coming out of the emitter, and if you look at the green strip around the outside, you'll see that if atoms are mostly empty space, it should go straight through. And I could see little golden shine marks on the direct opposite of the emitter. You could see straight across. Some are going straight through. But then sometimes, right, the beam itself, and remember, it's not just one particle. They're sending a whole bunch of particles out there. And some are bouncing back, right, towards the emitter, and some are veering off course, kind of down towards the bottom of the screen after the foil. So if you look at this animation for a second, right, on that fluorescent screen, those alpha particles lighted up in certain spots. It's not lighting up just on the end. It's lighting up on the sides. It's lighting up back towards the emitter. So something's going on here. So when we look at the results, sometimes the alpha particle itself goes through, and sometimes it bounces off of things, right? So when you look at the alpha particles sort of veer through, that's what I want to portray more. If atoms are mostly empty space, like you're seeing right now, that explains it. If atoms are more like a plum pudding, those alpha particles should always be bouncing back, like right now. Okay, so this is the model Rutherford's looking at, and this is the model right here that J.J. Thompson's looking at. Rutherford, Thompson. And what we saw in the experiment, now we can go back, is that these particles, formerly known as alpha particles, they literally are just from the element helium. They're the nucleus of the helium atom. But for the sake of posterity, to make it simpler, right, they're just positive charges. And what we saw, and that I'll elaborate up here now, is that a variety of things happened. So what really went down? Because it turned out that atoms are mostly empty space, atoms have a positive charge in the nucleus, like this. Positive, positive. Now, in this case, if these positive charges run directly in line with the nucleus, they're going to bounce off, and they're going to veer off course, and they'll come back and light up the screen that bends around on this side. If, alternatively, those alpha particles hit the nucleus, but not straight on, they bounced. and they went off course like this. And they ended up lighting up the screen over there. So that's a deflection, right? Like in hockey, the puck still keeps going forward, but it's been deflected. It bounced off something. In this case, it wasn't a stick or a glove or anything. It was the nucleus. In other cases, that electron beam, or sorry, rather that proton beam, that positively charged particle beam, if it went through what's mostly empty space, it lit up on this side. And in fact, you could see it's lighting up here as well, went straight through, right? It's lighting up here, went straight through. So what that tells you is that atoms have a nucleus that's positively charged, and that they're mostly empty space. Now, if I was to draw this more accurately, and I'll just do it up here, think of the nucleus as being this tiny thing, and the space around it as being just vast, empty. Although we know electrons do occupy that empty space, because electrons are outside the nucleus. So this very famous experiment really helped to define what it was that an atom was comprised of. An atom is a positively charged nucleus with a whole bunch of empty space, and there's these negative charges around the outside, which is very different than the plum pudding model. Now, at this point, the negative charges, we don't know exactly what space they're residing around that nucleus, but we know there's this positive nucleus, and that there's all this dead empty space, and there's these electrons. So you kind of get a planetary model, right? Which is one you're used to seeing. This kind of an idea, right? Where the electrons are whizzing around the nucleus like that. That's called a planetary model. Now, right now, we're not far enough along to talk about the origin of the proton, or rather the neutron. Rutherford determined that there was proton in there. And that they're positively charged. We knew about the electrons from J.J. Thompson's model, but neutrons, which are neutral, that's a separate experiment that we have to talk about. Now, talking about these, like howitzer shells bouncing off things, because there was deflection and reflection, it was said it was like watching howitzer shells bounce off things, which is interesting because you got to realize that the gold foil was extremely thin. So the nucleus is small, dense, and is positively charged. Three major things that Rutherford determined. So let's get out our checklist. Ooh. Discovered an atom is mostly empty space, that there's got to be a positive charge in the nucleus. Gotcha. That the nucleus, well, composed of neutrons. This is for a later day. Yes, you could say there's protons here, but neutrons, that's a separate discovery, right? Because they had no charge. To date, we've been using electrical current, and we've been using alpha particles to figure out about the negative pieces and the positive pieces. But what about the neutrons, right, that are neutral? No charge. That's a separate experiment worth discussing in just a brief separate video. But that these electrons were distributed around the nucleus, and he came up with that planetary model, right? This one, which I draw horribly. Get the idea? There we go. I'll adjust it so it looks a little bit better. There's our planetary model of the atom, or nuclear model of the atom. So, sort of come up on the evolution of the atomic model, although we can't really do them all justice. Oops. There we go. There was the Dalton pool ball model there, the billiard model. Thomson's discovery of the electron, right? Comes up with the idea of that maybe an atom is like a plum pudding. Rutherford does his gold foil experiment and determines that there's something positive causing alpha particles to veer off course and bounce back. And he extends the model to say that, well, there's probably what's going on here is these negative things are around here, and there's all this empty space, and that there's a nucleus. So here's our nuclear model, sometimes called planetary model. But later, and the things that we have to cover, what about, well, where do you find them? Like, if they're a little bit like planetary moons, do they have different orbits? And if you look at the Bohr model, you've done a little bit of in grade 9, there's an idea that these electrons can be in different, different orbits. So it sort of takes the planetary idea and pushes a little bit further, right? That one. But these are just all evolutions of understanding. Later on, when we look at the quantum mechanical model of the atom, we start to think about, well, if there's electrons, where could we probably find them? Like, if we're playing hide and go seek with electrons, where would we find them? And if we drew a map of where we found them most of the time, what's the most probable place for the location of those electrons? And, does it make a pattern? And some of these patterns are kind of cool. One electron probability pattern kind of looks like this, with the little bow ties being where we would find the electrons at different moments in time. Just probability mapping or behavioral mapping sort of for an electron. But that's for another day. So ladies and gentlemen, that's it. Thanks for listening and have a good one.